and welcome back to this second video in Covidenomics. In this class, we're going to be looking at the idea of exponential growth. Some of you may have heard that viruses, particularly in their early stages, tend to increase in terms of infections at an exponential rate. What does this mean? We're going to be exploring that in this video. We're going to be looking at the ideas behind exponential growth. We're going to be looking at some examples. In particular, we're going to look at an economic example relating to some Australian policy. And then we're going to finish up by thinking about why exponential growth may not be the best way to think about the course of infections over a pandemic, even though it may be useful for the early stages. To see why exponential growth is relevant for a virus, let's start off with a very simple example. So we're going to have a person who has a novel or a new virus and starts a pandemic. We're going to assume that the reproduction number, as it's called, for infections, R0, is going to be 2 here. What does that mean? Well, it means that one person who is infected will on average infect 2 other people. Think of it this way, they bump into 2 other people whilst they're infectious, and those 2 people catch the disease. Each of those people then bump into 2 other people whilst they're infectious, and they infect 2 people each, or 4 in total, and so on. So the progress of a virus is one person passes it on to 2, who each pass it on to 2 to make 4 new infections, to pass it on to another 2 each to make 8 new infections, up to 16, and so on. So what's happening with this virus is that each generation of infections is going up at the rate of 2. Or in other words, we start off with 2 to the power of 0 infections, 1 person, then 2 to the power of 1 or 2, 2 to the power of 2, 4 people, 2 to the power of 3, which is 8, 2 to the power of 4, which is 16, and so on. So that sort of process leads to a number of infected people that increases at an increasing rate over time. Sort of like what we've got here, time on the horizontal or x-axis, the number of infected people, the population size on the y-axis, and you'll see it's increasing at an increasing rate. There's already one tiny complication here in that we have to be clear about whether we're talking about the new infections or the total number of people that have ever been infected. If we just think about new infections, then we're going 1, 2, 4, 8, 16, and so on. If we're thinking about the total number of people who have ever been infected, then we go 1, 3, 7, 15, and 31, and so on. Now, in general, for a pandemic, what we really care about is the rate of new infections. So it's really the first of those. So in that situation, patient 1 has the infection, passes it on to 2 people, and then that patient recovers or dies and is no longer able to pass it on. Each of these 2 people pass it on to 2 people, and then they either recover or die, and so on. So let's look at the simple maths behind this exponential growth in the number of new infections in each generation. And we're going to do it for our example where R0, the reproduction rate, is 2. So first off, we start off with N0 in our example was 1 person, and the first generation of infected people is simply R0 or 2 times the initial generation number, which is 1, so just simply 2 in our example. Our second generation of infections, N2, is simply 2 times the first generation, 2 times 2, which is 4, or 2 times 2 times N0, which of course is just N0 times 2 to the power of 2. We can then consider our third generation of infections, which is just going to be R0 or 2 times N2, but N2 is 2 times N1, so it's 2 times 2 times N1, but N1 is 2 times N0, so it's 2 times 2 times 2 times N0. or in other words, n0 times 2 to the power of 3, and we could continue this for each generation of new infections. For our specific example here, that gives us the number of new infections in generation T is simply n0, our first or original generation of infectors, times 2 to the power of T. And we can extend this to a general reproduction rate R0, and note that the number of infections for this general reproduction rate, the number of infections in generation T, is simply the original number of infected individuals times R0 to the power of T. And this is just an example of our general exponential growth formula. Fx is simply equal to a constant A times B, the reproduction rate, to the power of x. So fx equals A times B to the power of x. Exponential growth often applies to populations, so let's consider our cute little bunny friend over here. A pair of breeding rabbits tends to have a litter of between 6 and 10, about 6 to 7 times a year, with a mortality rate of about 50%. So given this information, we can say that a pair of rabbits, let's say about every 2 months, has around about 8 other rabbits. About half of them die, down to 4. You need breeding pairs, so reduce it back to 2. So you've got an R0 about every 2 months of 2 for breeding rabbits. So after 1 year or 6 breeding generations, we'll have N6, which is just 2 to the power of 6, or about 64 pairs of cute little bunnies. After 2 years or 12 breeding cycles, we would have 2 to the power of 12, or 4,096 pairs of not quite so cute looking bunnies. And after 3 years or 18 breeding periods, you end up with a pretty horrifying 2 to the power of 18, or over 262,000 breeding pairs of, at this stage, vermin. Now, in most situations, this won't happen because rabbits will face predators in the wild, such as foxes, which will keep this population growth down. But when rabbits were introduced to Australia, they had no natural predators, and this sort of growth is exactly what happened, which is why rabbits are a notorious pest in Australia. Let's consider another example of exponential growth, this time applying to compound interest rates. Suppose you start off with $100 to invest, and let's say that your investment pays off an annual interest rate of 5%, and we'll use this little R here for the interest rate. After 1 year, you've got your principal of $100, but you've also received interest of 5% on that $100, or $5. So in total, you've got 100 times 1.05, or $105 at the end of the first year. Let's suppose you reinvest all of that. Well, at the end of the second year, remembering that you invested $105 at the beginning of that year, you get $105 times 1 plus R, but that's just 100 1 plus R times 1 plus R. But this is just the $100 you started off with times 1.05 squared, which is $110.25 at the end of the second year. Again, let's say you reinvest $110.25 for a third year. Well, at the end of the third year, you get $110.25 times 1 plus R, or in other words, 100 times 1.05 cubed, or $115.76. Or we can generalise this and just say that after T years of investing, you will end up with your original principal of $100 times 1.05 to the power of T dollars. So for example, after 50 years, you would end up with 100 times 1.05 to the power of 50, or around $1,146.74 for your initial $100 investment. And this is just an example of exponential growth, so we can fit it into our general formula. Here our R0, or our reproduction rate, is simply 1 plus the interest rate, 1.05 for a 5% interest rate, remembering that R here is expressed as a fraction. And our general formula is that the number of dollars you'll have after 2 years at an annual interest rate of R is simply your initial principal in naught times 1 plus R to the power of T. So compounding savings works on exponential growth. This compounding has been an issue for one of the Australian government's responses to the COVID-19 pandemic. One of the responses has been to allow people to access part of their compulsory superannuation savings. They've been able to access up to $10,000 in the financial year up to the end of June 2020, and they'll be able to access another amount up to $10,000 in the financial year July 2020 through to the end of June 2021. Now, some people have said that accessing this money is a bad idea. What's their argument? Well, it's based on this compounding. They've said if you access $10,000 now, sure, you'll have a bit more money to spend now, but it may be very, very expensive in the future. For example, just using our 5% interest rate here, if you've got 25 more years before retirement and you access your $10,000, then the lost retirement income for 25 years in the future is 10,000 times 1 plus R, so 5%, so 1.05, to the power of 25, just our little formula that we've got over here. What is that amount? Well, it's about $34,000. So the argument has been that if you spend the $10,000 today, it's going to cost you $34,000 in the future. Even bigger amount, obviously, if you're further from retirement. So say you've got another 30 years of working life ahead of you. Then, again, applying our compounding formula at 5%, that $10,000 today would mean about $43,000 less retirement income when you retire. So that's an interesting argument. I'm not sure it's very convincing because, after all, $1 today isn't the same as $1 in 25 or 30 years' time. And if you need the money today because otherwise you're not able to put food on the table, or you may not be able to pay the rent or something else, it's not very useful to say, but think of all the money you could have had when you retire. So it's an interesting argument, but I think the government's policy is probably pretty sensible. Let the people who need access to that money today, who have got it in their compulsory retirement savings, access the money today. And that will reduce the effect of the pandemic, not only on the individuals, but also on the Australian economy. So let me summarise what we've done in this video. We've looked at the rate of growth of infections, the spread of infections of a pandemic such as COVID-19. And we've noted that it follows an exponential pattern, or the rate of increase in new infections is exponential. And we've got a little formula that allows you to calculate that rate of increase, that rate of growth. We noted that exponential growth can be pretty dramatic. It can lead to a very quick increase in the number of infections, but that depends on this R factor. It depends on the reproduction rate. But it's this exponential growth part of a pandemic, of the infections, that makes it so dangerous. Because it's very easy for the pandemic to get out of hand very quickly, depending on that reproduction rate. And finally, we also looked at other situations of exponential growth. It's not just for pandemics. We noted that, in general, populations, such as populations of rabbits, increase according to exponential growth, so long as there aren't any constraints. We also noted that compound interest on savings follows a pattern of exponential growth. There's two things to take away from those last two examples. First is from the bunnies. Notice that it was unconstrained growth. We said that as the population of bunnies gets bigger, well, they become food for the foxes. There are natural constraints out there that push back against the exponential growth in the bunny rabbit population. There are also natural constraints that push back against exponential growth for a pandemic, and we're going to be talking about those in future videos. The second part to note is that this exponential growth depends critically on the reproduction rate. Unlike the bunny rabbits, our savings don't seem to get that big that quickly. Compounding matters, and we'll talk about that a bit more in the next video. But we didn't have explosive growth when we popped our money into an investment at 5% per year. We had good growth, sure, but it wasn't explosive. Why? Well, that's because the reproduction rate was much closer to 1. And we're going to find in future videos that that reproduction rate matters a great deal, not just for compound interest on your savings, but for the progress of a pandemic. Thanks for listening. Talk next time.